Okay, so for this video, we will be talking about the alkylation of 1,4-dimethoxybenzene. I will be doing part A, will be doing part B, and Marissa will be doing part C. So our introduction. The purpose of the experiment is to determine which isomers are formed from the alkylation of 1,4-dimethoxybenzene. The experiment utilized Friedel-Crafts alkylation, in which the most evident change is the formation of new carbon-carbon bonds. In the presence of an acid catalyst, ethylene and benzene react and form ethylbenzene and styrene. Once this occurs, tert-butylbenzene is wanted, in which the electrophile is the carbocation formed from the acid catalyst. And then the OH group is then removed from the tert-butyl alcohol, as seen in this photograph. For the mechanism, we can see that the benzene ring is temporarily stabilized due to the resonance, but becomes fully stabilized when the compound loses a proton. This causes the ring to be aromatic again. And then the methoxy group acts as an electron donating group and are ortho-para directing. It is very important to note that double the amount of alcohol is needed to push the reaction forward due to Le Chatelier's principle. Techniques that will be used in this lab are recrystallization and extraction. For recrystallization, it's used to purify an impure compound in a solvent. And here is a photo of the setup. Vacuum filtration is also used, and it is also used to purify an impure compound as a solvent. And here is the Buchner funnel and the setup used.
So for the procedure for this lab, we're first start off with 15 grams of dimethoxybenzene, 0.25 milliliters of 2-methyl 2-propanol, and half a milliliter of acetic acid in a flask, and warm it until the solids are all dissolved. After the solids are dissolved, I'm going to put the flask in an ice bath, and we're also going to add 1 milliliter of sulfuric acid in 13 test tubes and place all test tubes in an ice bath. While stirring the solution in the flask, we're going to add the sulfuric acid dropwise for 1 minute and then leave in ice bath for 6 minutes. And then 10 more minutes at room temperature. After that, we are going to add 5 milliliters of cold water. Once we do that, we're going to make the liquid product. We're going to add 2 milliliters of diethyl ether to the mixture in the reaction flask, then pipette the contents of the flask to a 15 milliliter centrifuge tube. From then, we're going to remove the lower aqueous phase from the centrifuge with pipette and add it to a 250 milliliter beaker with 50 milliliters of water. We are then going to wash the remaining ether layer first with 2 milliliters of water and then 2 milliliters of saturated sodium bicarbonate solution, and wash the ether layer again with 2 milliliters of water. After that, we're going to remove the last aqueous wash, dry the ether solution with anhydrous sodium sulfate for at least minutes. And then step 5, we're going to weigh our product, then transfer the dried ether solution to a weighed 13 by 100 milliliter test tubes, 13 100 millimeter test tubes using a Pasteur filter pipette, and we're going to evaporate the ether and weigh. The next step is making a solid product. So we're going to vacuum filter the solution with a Hirsch funnel. We're going to chill 1 milliliter of methanol in a small test tube. We're then going to wash the crude product 3 times with 1 milliliter of water. We're going to wash the product 2 times with half a milliliter of cold methanol. It's important to disconnect the vacuum, cover the crystals with the cold methanol, and then reconnect the vacuum. We're going to then transfer the crude product to a 10 milliliter Erlenmeyer flask, and we're going to recrystallize the product from a minimum amount of methanol. And then we're going to collect the product by vacuum filtration. So from the product collected, it was seen that the physical state of the product was a solid. It was a white powder-like substance. Before the recrystallization process, the melting point was found to be 98 to 102.5 degrees Celsius. After recrystallization, the melting point was found to be 103.5 to 104.5 degrees Celsius. And the theoretical melting point was found to be 102 to 104 degrees Celsius. So in the calculations, the mass of 1,4-dimethoxybenzene used was 148 milligrams. The volume of tert-butyl alcohol used was 0.24 milliliters. The amount of sulfuric acid used was 1 milliliter, and the product obtained was 200 milligrams. And the limiting reagent was 2-methyl-2-propanol. And after calculations, we found that the percent yield was found to be 72.6%.
So when we are looking at the IR, this is going to be, all our spectra are going to be of the major product. So that would be 2,5-ditert-butyl 1,4-dimethoxybenzene. So when we look at our IR, we see that we have 4 major peaks. Our first one is at 2,994.05. It's weak, but it's sharp, so that means that we have a CHSP2 stretch. The one right next to it at 2,950.93 is moderate strength and also sharp, so that means we have a CHSP3 stretch. And finally, the 2 signals, one at 1,503.49 inverse centimeters, and the other at 1,450.19 inverse centimeters. Those are both sharp, one is weak and one is moderate, and those both indicate a C double bond C stretch. So when we look at our broadband decoupled carbon NMR, we have our peak with the highest integration at 29.87 parts per million, showing that we have a tert-butyl. So all those are going to be carbon A. The shift at 55.98, those are the carbons on the methoxy group. And the peaks furthest downfield indicate the carbons that are attached to the benzene ring. For our proton NMR, we have a singlet at 1.3663. It has an integration of 9, which is consistent with tert-butyl groups. So again, that would be proton A. The singlet at 3.8101, which is proton B, correlates to the hydrogens attached to those methoxy groups, and the singlet at 6.8328 is consistent with protons located on the benzene ring, which would be protons C. When we look at our DEPT 135, 90, and 45 NMR spectra, we only see CH and CH3 peaks because 2,5-ditert-butyl 1,4-dimethoxybenzene only has CH bonds and CH3 bonds. So the aromatic peak shows up around 130 parts per million, which we can see is the CH bond. As for our COSY NMR, we can see that nothing is coupled here because nothing correlates with it with anything else outside of that diagonal axis. And that'll do it for our alkylation lab.